This is the first section of chapter 2, which is all about allocation problems. And in this first section, we're going to be looking at the Hungarian algorithm. So this algorithm and others like it, or allocation algorithms in general, seek to allocate workers to tasks or tasks to workers to maximize or minimize costs. Now put workers and tasks in quotes because they may not necessarily be called workers or tasks, but it's about allocating one thing to another. And I've put costs in quotes because the costs, for example, may be distances. They may not necessarily be something of monetary value. But the idea is allocate one set of things to another, either to maximize a cost or to minimize a cost. So let's have a look at what this Hungarian algorithm is. Now, just like other algorithms, it makes more sense when you go for an example, but I want to list all of the steps here. So in these types of questions, we'll have something called a cost matrix, which basically tells us the cost associated with allocating each worker to each task. And the first step is going to be to find what we call a reduced cost matrix. Now, the first two steps are that we subtract the smallest value from each row from every element in that row. This is called row reduction. Then we subtract the smallest value from each column from every element in that column, and this is called column reduction. The next step is to draw the minimum number of horizontal and vertical lines through the reduced cost matrix to cover all of the zeros. Now, to help speed up this process, because this is going to be an iteration process, or maybe we need to go through steps again, to minimize those numbers of steps, when we carry out this step here, we want to try to make the minimum uncovered values as large as possible. Then in the next step, we look to see at the number of lines we've used, and if the number of lines that we've used equals n, where the size of the matrix is n times n, so these are going to be square matrices, so n and m are going to be the same number. So let's say it was a 5 by 5 matrix and we've used 5 lines, then we found an optimal solution. The solution is optimal, and at this point we end. Now this next step here is only required if we don't have an optimal solution, and what we do is we add the smallest uncovered element, which we're going to call E, to every element covered by 2 lines. That's the lines that we drew in this step here. And then we subtract E from every element not covered by any lines. Now what that means is that if we have any elements covered by just 1 line, they should remain unchanged. And then the iteration part is now from this step, we go back to this step here, and we keep looping around these steps until we've got an optimal solution. And by carrying out this step here, by making the minimum uncovered values as large as possible, it minimizes the number of times we need to iterate and go around these steps here. Now, just a little word about doing our allocations. Quite often we can sort of look at the cost matrix that we've got and allocate workers to tasks once we found an optimal solution. But where there's a single zero in a row and column, then we must assign that worker to that task. Okay, so now let's look at some examples. Example 1. The table shows the times taken in minutes by 4 workers to complete each task of a 4-stage production process. Okay, so here are workers, here are tasks, and these are the times taken for each worker to complete different tasks. And what we want to do is to allocate each worker to a task that minimizes the time taken. In other words, reduce the cost matrix. In other words, here the cost is time. So I'm going to transfer the headings from the cost matrix into this matrix here. And my first step is to do row reduction. So what that means is I find the smallest value in each row and I subtract that value from each row. So I'm going to highlight them. So the smallest value in the top row, is 12. So that means I need to subtract 12 from every element in that row. I'm not sure why it keeps coming up with the pen. I just want to highlight it. Here we go. Second row, the smallest value is 14. So I'm going to subtract 14 from each of those values. The third row, the smallest value is 13. And in the last row, the smallest value is 10. So this is what I subtract from each row. So starting with the top row, I subtract 12 from each of those values. So 12 minus 12, 23 minus 12, 15 minus 12, and then 40 minus 12. Now, if this is done correctly, the element that you've chosen should become 0. So after we've completed this, these values that I've highlighted should be zeros in this matrix here. Second row, I now subtract 14 from each of those values in each row. So the 14 becomes 0, 21 becomes 7, 14 becomes 3, and 20 becomes 6. Next row, I subtract 13 from each of the values in the third row. So 0 to 13 becomes 0, 22 minus 13 is 9, 20 minus 13 is 7, and 30 minus 13 is 17. Then the bottom row, I subtract 10 from each of these values, leaving me 4, 14, 3, and 0. So that completes my row reduction. So now I'm going to complete my column reduction. So I find the smallest value in each column and subtract that from every element. Now, the first column, the smallest element is 0. So I'll be subtracting 0 from each of those. So that's not going to make any difference. The second row, the smallest value is 7. That's going to get subtracted from every value in that column. Third column, it's 3, any one of those 3s. And the last one, the smallest value again is 0. So those values are going to remain unchanged. Right, so first column, subtracting 0 from every element, they remain unchanged. Second column, subtracting 7 from each of those values, 11 minus 7, 4 minus 7, 9 minus 7, 14 minus 7. Then the next column, subtract 3 from every element, so 0, 0, 4, 0. And the last one, I'm subtracting 0 from any element. Now do watch out. It's tempting to forget the 0 and say, oh right, 6 is the smallest element. So do watch out for those zeros. So what we've got here now is our reduced cost matrix. Now we don't need to go any further with this question. We've done the reduced cost matrix, but just to show you what we would do if we need to allocate workers to tasks is I'll say, right, how many lines do I need to cover all the zeros? The minimum number of lines. So 1, 2, 3, 4. Now there may be other ways of covering all of the zeros, but I can't do it in less than 4 horizontal and vertical lines. Now since this is a 4x4 grid, this tells me actually this is an optimal solution. 4x4 grid, and we've used 4 lines. And then we would go about allocating workers to tasks. Now where we've got like a single 0 in a row or column, then we must allocate that worker to that task. So for example, I can see that in this first column that I could allocate task W to any one of these 3 people here, Chris, Laura or Sam, because there's a 0 here. But when I get to the second column, I can only allocate Laura to task S because that task X, because that's the minimum cost. So let's just highlight that. I'm going to allocate Laura to task X. Then if I look at the next column, I could allocate task Y to Chris, Laura or Steve. Okay, but when I go to the last column, task Z, I want to allocate to Steve because that carries the minimum cost. So we'll just highlight that. We'll allocate those. So basically we've used up task X and task Z, and we've used up Laura and we've used up Steve. So now it's just a matter of saying, right, who are we gonna, what task are we gonna allocate Chris to, and which one Steve. Now Steve, we've got a 0 here. So Steve, I would allocate to task Y, like that, and use that up. Sorry, my mistake. We've already used Steve, haven't we? So actually, it should be Sam allocate to task W, because that's where the only 0 is there. And then that means Chris has to be allocated to task Y. And then from here, what we do is we look at the original cost matrix, and we can work out what the total cost is by looking at who we've allocated to what. Sam to W, so that's 13. Laura to X, that's 21. Chris to Y, that's another 15. And Steve to Z. So our total cost for this one, if we were asked to do it, we only had to do the reduced cost matrix. 13 plus 21 plus 15 plus 10 gives a cost of 59 minutes. Example 2. Barbara, Percival and Spike do gardening maintenance. The table shows the times in minutes that they would take to do each task in Mrs. Green's garden. Allocate the task so that the time taken to do the whole job is as small as possible. So here again, costs is time. These are our workers and these are the tasks here. Okay, so let's start first of all with our row reduction by finding the smallest value in each row. So the top row, the smallest value is 80. Middle row, smallest value is 90. And the bottom row, smallest value is 110. So we're going to subtract those values from each value in each row. So the top row, we take away 80 from 250. So you got 170, 80 from 80, and 80 away from 160. And we take 90 away from 230. We take 90 away from 90, 90 away from 150. And at the bottom row, we take 110 away from each value. So we've got 120, 0, and 30. So there's our row reduction. So now we do our column reduction. I want to find the smallest value in every column. So in the first column, smallest value is 120. Second column, they're all zeros, so any 0. It's not going to make any difference. And the last column, 30 is smallest value. So first column, let's start by taking away 120 from each of our values. So 170 minus 120, 140 minus 120, 120 minus itself. These zeros won't change. And then we take away 30 from each of the values in the last column. So that completes our column reduction. So now we draw the minimum number of lines to cover all of the zeros. Now we have to use 2 lines. So that tells us that this solution is not optimal because we want to be able to do it in 3 lines. So we now need to improve or augment this reduced cost matrix. And the way that we do that is we look for the smallest uncovered element, which we call E. So that's going to be 20. That's the smallest uncovered element. And what we do is any elements that are covered by 2 lines, we're going to add E. So we're going to add 20 to this element here. Any other uncovered elements, we're going to subtract E. So we're going to subtract 20 from these elements here. And the elements which are covered by 1 line remain unchanged. Okay, so let's start with the elements covered by 2 lines. So this one here, we need to add E to that. So we're going to add 20 to it, so that becomes 20. Let's move on to the elements covered by 1 line. They're going to remain unchanged. So they're going to stay as 0, so 0 here in these boxes. And the other uncovered elements, these 4, we need to subtract E. So we're going to take 20 away. So we'll have 30, 0, 30, and 10. Now, with this, the minimum number of lines needed to cover all of the zeros is 3. So we've now found an optimal solution. So I'll just write down this is optimal. And since it's optimal, we can start allocating workers to tasks. So since there is only 1 0 in this column, that means we're going to allocate Spike to deal with cutting the lawn and hedges. And that is a cost of 140 minutes. So Spike and cutting lawn and hedges is dealt with. I think I might actually highlight this a different way so I don't end up picking people twice. Okay, so that's used up. If I look at what's left, well, Percival must be allocated to dig in the vegetable patch, and that's going to be at a cost or a time of 230 minutes, which then just leaves Barbara has to be allocated to weeding flower beds, and that's at a total cost of 80 minutes. So I've got my allocation here. I'll just write down what the total cost is in time. So that's going to be 140 plus 230 plus 80, and that gives 450 minutes. So always state what person you're allocating to what task and the total time cost associated with those allocations. Example 3. 5 workers, Ben, Ellie, Greg, Hayo and Toby, are to be assigned to 5 tasks involved in making a soft toy. The table shows the times in minutes taken to complete each task. Reducing rows first, using a Hungarian algorithm to determine an allocation that minimizes the total time. Okay, so let's start by finding the smallest element in each row. So first row is going to be 3, second row 5, any of the 5s, then 3, then 2, then 2. So top row, let's take away 3 from all of those, so 6, 5, 0, 3, 7. Second row, let's take away 5, so 0, 0, 2, 0, 0. Third row, we'll take away 3, so 7, 6, 0, 6, 7. Next row, take away 2. And the bottom row, we take away 2, so 7, 6, 0, 5, 8. Now next we would do the column reduction, but if you have a look, the smallest element in each column is 0. Okay, so we don't need to do column reduction. It's not going to make any difference. I'll just write that down. So no column reduction is needed, as every column has a 0, so it's not going to make any difference. So now we can go straight on to drawing the lines to cover the zeros. Now there's only zeros in the middle column and the top row. So 2 lines are needed. Since this is 5 by 5, we would need 5 zeros. So this is not optimal. So now we need to augment the matrix, which means that we find the smallest uncovered element, which we call E. And I can see that that is 3. That's the smallest uncovered element, 3. So what that means is I need to add 3 to this element here, covered by 2 lines. The other ones remain unchanged, covered by 1 line, and every other element I now subtract 3. So we'll add 3 to the 2 covered by 2 lines, so that then becomes 5. These other ones, which are covered by 1 line, they remain unchanged. And then all of the other elements we subtract 3. So we will have 3, 2, 0, 4, if my subtractions are right. Then Greg and Cut take away 3 is 4, 3, 3, 4. Next row down, taking away with 3 is going to be 5, 2, 4, 2, and in the bottom row 4, 3, 2, and 5. Now we need to cover the zeros with the minimum number of lines. Now there are different ways we could do it. I could do it this way, cover those zeros and cover that. That's 3 lines. Or I could, I suppose, draw a line through here, and through here. Whichever way I want to do it, I want to try and leave the minimum uncovered element as large as possible. Now, it doesn't matter which arrangement I use, the minimum uncovered element will be 2. I can't cover up all of these 2's and leave like the minimum as 3 or 4. So that's not possible in this case, but if you can do it, try and cover those minimum elements with the lines. I can't really do that. If I cover this 2, so let's take these lines out. So if I were to draw a horizontal line to cover this 2 and draw a line here to cover those zeros, then you'll see that there are other 2's here that are uncovered. I can't cover them all in this case. Now, putting that to one side, I don't have an optimal solution. I would need 5 lines. So this is not optimal. So I augment my matrix. I find E, the minimum uncovered element, and that's going to be one of these 2's. There are plenty of 2's in the grid. So you can see that, you know, if that minimum uncovered element was larger, then that's going to make a difference to what we sort of add and subtract to the other elements. Okay, so what do we do now? Those elements which are covered by 2 lines, we add E, and those which are uncovered, we subtract E. Right, so let's fill these in. So that 0 and that 5, we're going to add to those 2. So that becomes 2 and 7. All the other elements covered by 1 line remain unchanged. So 3, 2, 0, 4, 0, 0, 0, 0, and 0, 0. And the other elements we're going to subtract 2. So we have 2, 1, 3, 0, 2, 1 here, and 1, 2, 2, 0, 0, 3. So now I cover my zeros in a minimum number of lines possible. I can't really do it in a minimum number of lines and cover up these ones or the lowest value elements. So I can see here that this is not optimal. And in this case, my smallest uncovered element, E, is going to be 1. So I'll clear up the first grid so that we can then work on this or augment the matrix. So we're going to add 1 to these elements that are covered by 2 lines. So that means that 7, Ellie and Phil, will become 8. And then the 0 will become 1. And then Hio and Phil, which has 0, that becomes 1. And the 2, Hio and Finish, becomes 3. All those other elements covered with 1 line don't change. So 2 and 0 there. 0, 0, 0. And then I think on the next row down, the 0 and the 1, they don't change. And the bottom row, the 0 and the 0. And then also the 3, 0 and 0 here. I think that's right, that follows the same pattern. And then all those other elements take away 1. So 2, 1, 3, 1, 0, 1, and bottom row 1, 0, 2. Right, let's see how many lines we need to cover all of the zeros. So lots of zeros there. So 1 line there, 1 here, so that's 2. Need to cover this 0 here, 3, 4, 5. I can't do it in any less than 5. So that means that this is optimal. So now I can allocate people to tasks. Right, so let's look for a row or column that just has 1 0. So here, so Ellie, I'm going to allocate to cut. So we'll get rid of Ellie and we'll get rid of cut. And we'll write that down. Ellie is going to cut. And if I look at the original table, Ellie and cut has a cost of 5 minutes. And if I look at the top row, there's a single 0 here, so Ben has to finish. So we'll get rid of Ben and finish. Get rid of that row and column. So Ben, finish. And if we look at the original table, if Ben is going to finish, that's a cost of 6 minutes. Now, if we look at the remaining people and tasks, because there's not a single row in each row or column, we have choices. So, for example, Hayo could sew or pack. And if we look at the cost, that's not going to change his cost. It's still going to be 7. However, for Greg, he could sew or fill. Now, if we get Greg to fill and pick his lowest cost of 3, that means Toby's cost is going to be higher. Or if we choose Greg to sew and then Toby fills, then the cost change. But notice the difference between them is 6. The total cost isn't going to change. So we've got choices. I'm going to pick Hayo. He's next. So Hayo, let's get him to pack. I think I have to get him to pack. No one else can pack yet. So Hayo, not Hypo, Hayo is going to pack. And that's a cost of 7 minutes. So really that's the one we have to assign. So Hayo, let's get rid of him in the pack. So the choices come with Toby and Greg. They can do either task. The overall cost isn't going to change. So let's get Greg to sew. I'm sure he's going to enjoy sewing. That's a cost of 9 minutes. And then we'll get Toby to fill at a cost of 2 minutes. So even if I had changed the order in who I allocated, then Greg would have a cost of 3 and Toby would have a cost of 8. It still comes to a cost of 11 minutes either way. Okay, so let's work out the total time by adding these together. 5 plus 6 plus 7 plus 9 plus 2. And that gives 29 minutes for our final cost. So I'm just going to highlight the final total cost and the allocation, who we've got allocated to these different tasks. And as I said, Greg and Toby, they could swap tasks at no additional cost. So you should now be able to do exercise 2A on pages 48 to 49. And here's a recap of the Hungarian algorithm.